Okay, good morning. Today we'll be learning about fourth unit. In the fourth unit, the first topic is plane stress and plane strain. What is plane stress? Now you have learned three stresses, three direct stresses and three shear stresses, that is sigma x, sigma y, sigma z are direct stresses. Shear stresses are tau xy, tau yz, tau zx. Now when you take consideration into plane stress, your z direction stress won't be there, that is sigma z will not be there. This condition is an example for if you take example problems of slabs, shells and plates. You can see this type of condition. Whenever you are having a plane stress condition, your sigma x, sigma y, sigma z is related to epsilon x, epsilon y, tau xy. Sigma x, sigma y, sigma tau xy is equal to epsilon by 1 minus mu square, e by 1 minus mu square into 1 mu 0, mu 1 0, 0 0 1 plus mu by 2, which should be multiplied by epsilon x, epsilon y, tau xy. Of course here it is given minus epsilon alpha t by e alpha t by epsilon y, 1 1 0. This is a temperature effect is there, you have to take into consideration. Now in plane stress condition, mind you, sigma z will be 0 but epsilon z will not be 0. There exists epsilon z which is given by epsilon z is equal to sigma z by e minus mu by e into sigma x plus sigma y. Sigma z dependent quantity we are not including in the problem though it exists. Say the example is you take a thin shell. Thin shell means thickness direction won't be there. You have two-dimensional problem. Na? Such problems will be taken into consideration for plane stress condition. Now let us take plane strain condition. What is plane strain condition? Plane strain condition is characterized by using very large direction. In one direction it should be large. Suppose you take a dam. What in the dam one direction is very large compared to other two directions. Other examples are retaining walls, tents, etc. In such conditions, your plane strain, you know that normal strains are epsilon x, epsilon y, epsilon z, and shear strains are gamma xy, gamma yz, gamma zx. Since it is plane strain, your epsilon z won't be there, and gamma yz and gamma xz also won't be there. Now there will be a relation between epsilon x, epsilon y, gamma xy to sigma x, sigma y, gamma xy. The relation is epsilon x, epsilon y, gamma xy is equal to 1 by e, 1 minus mu 0, minus mu 1 0, 0 0 2 into 1 plus mu, sigma x, sigma y, sigma z plus alpha t 1 1 0. This alpha t 1 1 0 indicating temperature stresses. Now, this type of problems, plane strain problems, involve body who have loading does not vary significantly. Like if you see a dam problem, loading will be uniform. Such problems are characterized as plane strain problems. Now, this is one more relation. You are given a relation epsilon x, epsilon y, gamma xy to sigma x, sigma y, sigma tau xy. This is the relation given. Suppose in the plane strain problem in the examination, if you are given sigma x, sigma y, tau xy, how we will do the problem? So for that, this is the relation sigma x, sigma y, tau xy is equal to epsilon by 1 plus mu into 1 minus z mu, 2 mu, 1 minus mu, mu 0, mu 1 minus mu 0, 0, 0 into 1 minus 2 mu by 2 into epsilon x, epsilon y, gamma xy. Again minus E alpha t by epsilon y 1, 1, 0. This indicates temperature stresses again. Now let us in a stretch, the main aim is whenever there is a problem, if you want to solve an elastic problem in the form of theory of elasticity, you can apply plane stress or plane strain provided those are two-dimensional problems. Let us take a difference between plane stress and plane strain problem. In the plane stress problem, your sigma x is equal to f1 of xy, which indicates your sigma x exists. Similarly, sigma y is equal to f2 of xy, which indicates your sigma y also exists. Again, tau xy is equal to f3 of xy. What is this f1, f2, f3? f1, f2, f3 are functions. Now, sigma z is equal to 0. Similarly, tau xz, as I said earlier, tau yz is equal to 0. Now coming to plane strain problem and plane strain condition, your epsilon x, f1 of xy exists. Then epsilon y, which is equal to function of x and y, some function of x and y, it exists. Then gamma xy, that is f3 of xy, it also exists. Your epsilon z is 0, gamma xz and gamma yz is also 0. This is about the difference between plane stress and plane strain. Here examples are given. For plane stress problem, thin plate, I already told thickness will not be there. Now example of plane strain problem is dam. Now, so sometimes in the examination they will be giving problems on plane stress, plane strain. Let us take one example problem given here. Stress at a point is given. Sigma x is equal to 2x square plus y. Sigma y is equal to 2x plus y square. Tau xy is equal to x plus y. Now a point P is given 4, 2, which indicates x, y. Now what is asked here? Find out strains in the plane stress condition and plane strain condition. So let us try to find out sigma x. Sigma x is given by 2x square plus y. So instead of x you substitute 4, 2 into 4 square plus 2, which is given as 36. Then sigma y, 2 into 4 plus 2 square, which is given as 12. Now tau xy, x plus y, 4 plus 2, 6. So you had the values of sigma x 36 MPa, sigma y 12 MPa and tau xy 6 MPa. Now what is asked in the question? Stress at a point is given. You have to find strains in plane stress condition and plane strain condition. Now let us take plane stress condition. Already you know this equation, sigma x, sigma y, tau xy is equal to E by 1 minus mu square, 1 mu 0, mu 1 0, 0 0, 1 plus mu by 2, epsilon x, epsilon y, gamma xy. Now for sigma x you substitute 36, sigma y 12 and tau xy it is 6. Then 1 mu is Poisson's ratio, all of you know. Poisson's ratio for steel is 0.3, that is known. So instead of mu you substitute 0.3. Then your matrix is equal to 36, 12, 6, then 1 minus mu square. What I have done here is, I want epsilon x, epsilon y, gamma xy. So I have inverted the matrix here. Once I inverted it, I will get 1 by mu square. Right? So here I can write here 36, 12, 6. Then 1 minus, instead of mu 0.3 square by E 2 into 10 power 5, 1 0.3 0 0.3 1 0 0 0 1.32 and its inverse. Then you will get epsilon x, epsilon y, gamma xy. Now if you solve the inverse in a classical method, I have chosen this method. You take an identity matrix and make it an inverse. So I had made row operations and column operations as given below. Finally, I got an identity matrix and I got the values like this. Now, substitute the values in the given matrix, inverse matrix. Then you will have 36, 12, 6 multiplied by 0.455 into 10 power 5 into your inverse matrix 0.901 minus 0.3270, 0.33, 1.090, 0, 0, 1.54, which is equal to epsilon x, epsilon y, gamma xy. Now if you multiply, finally you will get your answer as epsilon x is 12.9 into 10 power minus 5, epsilon y is 11.3 into 10 power minus 5, gamma xy is 4.2 into 10 power minus 5. As said, alternatively we have an equation here now. Let us go back once like this. You can use the direct equation like this: epsilon x, epsilon y, gamma xy is equal to 1e 1 minus mu 0. This equation also you can use and you can solve. So to make you understand how to inverse and recall the concepts of mathematics, I have given the example here taking the matrix method. Now let us take plane stress condition. It is a plane strain condition is epsilon x, epsilon y, gamma xy, which is equal to 1 by e 1 minus mu 0 minus mu 1 0 0 0 2 into 1 plus mu sigma x sigma y tau xy. It is directly substitute the value. Here E is modulus of elasticity. You know, for Young's modulus of elasticity of steel is 2 into 10 power 5. So you substitute the value. Instead of mu you substitute 0.3, then solve the matrix. Then you will get epsilon x is equal to 16.2 into 10 power minus 5, epsilon y is equal to 0.6 into 10 power minus 5, gamma xy is equal to 7.8 into 10 power minus 5. With that, problems of such sort will be coming into your examinations. Now let us take the next topic of our lecture. This is differential equations in polar coordinates. In the previous unit you have learnt equations in Cartesian coordinates. Here in this chapter we will be learning equilibrium equations in polar coordinates. What are the equilibrium equations? What is its significance? Suppose a body is there, a body is there, it has been subjected to some forces or loads. Now stresses will be developed. Now the stresses developed can be solved using these equilibrium equations. We will have 3 equilibrium equations for which 3 unknowns can be solved. In simple terms, you can see, suppose a beam loaded with UDL or a point load. You know that you will be having shear force, bending moment, deflection, deflection in x direction, deflection in y direction, deflection in z direction. So then you will have theta x, theta y, theta z. You know the theta is the slope. So you can solve the slope, deflections using these equilibrium equations. Any 3 unknowns can be solved. Either 3 deflections you can solve, either 3 thetas you can solve. That is slopes. Now let us take polar coordinates. Unlike our Cartesian coordinate system, in Cartesian coordinate system we will have only sigma x, sigma y, sigma z, that is stresses in x direction, y direction, z direction. Here polar coordinates you are newly introduced. You will have r, theta, then that is r and theta. Those are the two coordinates you will be having. Now let us take a strip of a circle which is given, that is arc of a circle which is given in the figure shown. Here you will have r is given, that is so in the direction of your radial direction your stress is sigma rr. In the direction of your radial direction your stress is sigma rr. Now like our sigma x, sigma y. Now in the other direction you will have sigma theta theta. Suppose you say sigma rr as sigma x, like similarly sigma theta theta is sigma y. Now sigma z should be in thickness. This is two dimensional. You will have tau x y na. So sigma r theta you will be getting. Now let us take the stress distribution pattern. So one direction it is sigma rr. So naturally the opposite direction will be subjected to little more stress. As said earlier classes, sigma rr plus dou sigma rr by dou r into delta r. This dou sigma rr by dou r into delta r is the extra stress subjected by the body in radial direction. Similarly, I told other direction stress is sigma theta theta. If one direction it is subjected to stress sigma theta theta, other direction it is subjected to stress sigma theta theta plus dou sigma theta theta by dou theta into delta theta. You observe this dou theta theta is varying in terms of theta only, because we are derivating with dou theta na, that is what. Now let us come to shear stresses. Shear stresses are naturally sigma r theta only. Sigma theta or sigma r theta is one and the same. So if one direction it is sigma r theta, the other direction it is sigma r theta plus dou sigma r theta by dou r into delta r. If this is in the radial direction, you will have shear stresses. Now other direction also you will have shear stresses, that is again sigma r theta, and other direction it is sigma r theta, other face it is sigma r theta plus dou sigma r theta by dou theta into delta theta. These are the stresses. Now equilibrium equations, like x direction, y direction, z direction will be adding. Here we will be adding radial direction, other direction tangential direction, we will be adding the stresses. Now summing of forces I said in radial direction leads to, let us know what are the forces in radial direction. The first force is sigma rr. This is radial direction sigma rr plus dou sigma rr dou r into delta r. This is first force. That is stress. Now you want to get stress na, stress into area is equal to force. What is the area? R plus delta r into delta theta is the area, right? Similarly, other one direction it is positive, other face it should be negative. So the other face the stress is sigma rr. Sigma rr is the stress into area is equal to r delta theta. This is stress. Now let us take in theta direction, that is radial direction, not radial direction, theta direction, circumferential direction. In circumferential direction you will have the first stress will be sin delta theta by 2 into sigma theta theta plus dou sigma theta theta by dou theta into delta theta into delta r, minus force will be again sin delta theta by 2 into sigma theta theta into delta r. That is sine component, because it is inclined na. So again you will have cos component. Now cos delta theta by 2 sigma r theta plus dou sigma r theta by dou theta into delta r. minus cos delta theta by 2 into sigma r theta delta r is equal to 0. Now, for small elements, if you take sin theta is theta, cos theta is 1. So, by dividing the entire equation by delta r delta theta, these are common, no? Delta r delta theta, you divide and you take sin theta is as equal to theta and cos theta is equal to 1. This all component is 1. 1 minus 1 that comes to 0. This all will be ruled out. Then what will be remaining? This one will be there. Here sigma rr and here sigma rr gets cancels. You will be reminded with dou sigma rr by dou r into r plus delta r plus sigma rr minus sigma theta theta minus delta theta by 2 into dou sigma theta by dou theta plus dou sigma r theta by dou theta is equal to 0. Now, as the limits delta r and delta theta tends to 0, then you will have equations in this form. Dou sigma rr by dou r plus 1 by r, dou r theta by dou theta plus 1 by r, dou rr minus dou theta theta is equal to 0. This is in the radial direction. In the other direction, if you solve the same manner, you will have dou sigma r theta by dou r plus 1 by r dou theta theta plus dou theta plus dou r 2 sigma r theta by r is equal to 0. This is broadly about equilibrium equations in polar coordinates. Now let us take one example problem, how we will solve, if a problem is given, how we will solve it using theory of elasticity methods. Let us take bending of cantilever loaded at its end. So as you know that whenever a cantilever is loaded at its end with a point load, you know bending moment is equal to PL, deflection delta is equal to PL by 3EI. You have solved in your strength of in the structural analysis by different methodologies. Now let us see how we will solve here. Here a cantilever is taken like this, right? X-axis is 0, above x-axis the distance is c, below x-axis the distance is c, a point load is loaded at its end. Now the entire length is L, that is span length. Now by experience you should take an polynomial equation that is second degree equation. You make alpha 2 is equal to C2 is A2 is equal to C2 is equal to 0. Then you in a second degree polynomial, you know the polynomial 1 plus x plus y plus xy plus x square, so on and so forth. That is alpha 1 plus alpha 2x plus alpha 3y plus alpha 4xy, so on. Alpha 5x square y square, that will be polynomial. In such a polynomial, you take a second degree polynomial, make a2 and c2 is equal to 0, add a fourth degree polynomial which have a4, b4, c4 and e4 equal to 0. Now adding such polynomials, you will get a function phi is equal to b2xy plus d4 by 6 xy cube. Now in the Aries function, we have understood that sigma x is equal to dou square phi by dou y square. Now you differentiate this phi with respect to y twice the above equation. You will have dou square phi by dou y square is equal to d4xy. Similarly, you differentiate phi equation with respect to x twice, you will get sigma y. Now if you differentiate the above equation with respect to x twice, you will get 0. Therefore my sigma y here is equal to 0. Now let us take tau xy. Tau xy from Airy's function is equal to minus dou square phi by dou x dou y. So if you take if you derivate phi again with respect to x1s with respect to y1s, you will be ended with minus b2 minus d4 by 2 y square. Now the following boundary condition must be satisfied. So whenever you are derivating, you got constants na b2 d4. Now these constants should be evaluated. You have to evaluate using some boundary conditions. All of you know that cantilever shear, you know that at the cantilever fixed end your movement is 0, your deflection is 0, slope is also 0. Here one more you have learned in your structural analysis. But here you take a condition shear stress. Shear stress at boundaries is equal to 0. Now let us go back to the problem. C at the C, that is at the boundaries, shear stress is 0. Now tau xy is equal at x plus or minus c is equal to 0. You substitute the condition. 0 is equal to, you know, tau xy is equal to minus b2 minus d4 by 2 y square, d4 by 2 y square. But instead of y you have to substitute c, because tau xy at y is equal to plus or minus c na. Then you solve this, you will get d4 is equal to minus 2b2 by c square. Now let us take other boundary condition. From minus c to plus c, tau xy dy is equal to minus p. That is natural because your shear stress is directly related to load. Now therefore again you substitute tau xy in the condition minus c to plus c minus b2 plus b2 c square y square dy is equal to minus p. You solve this integration, you will get b2 is equal to 3 by 4 p by c. Hence, now you substitute your constants d4 and b2 in the equation sigma x and tau xy. What you will get, we will see. Now if you substitute back, then sigma x is equal to minus 3 by 2 minus p by c cube x cube, which is equal to, right, minus pxy by I. Px into y is movement, my into I. But here we have taken some term 2 by 3 into c cube, that is represented as I. Anyhow, the moment of inertia of that particular member, where I is equal to 2 by 3 c cube, moment of inertia of the beam. Similarly, your sigma y is already 0. Now tau xy is equal to minus 3p by 4c into 1 minus y square by c square, which is equal to minus p by 2i into c square minus y square. Now these are equations sigma x and tau xy. These equations will have general solutions, right? Okay. Now let us, what is our aim? We want to know the displacement of the particular cantilever beam. How you will know the displacement? If you know strain, you will know displacement, because strain, you know, epsilon x is equal to dou u by dou x, where dou u indicates displacement in some direction with respect to x. Displacement in with dou u by dou x. Dou u means u is the displacement in u direction, in x direction, that is with respect to x direction. Let us take, we want u of x, that is displacement. We know that dou u by dou x is equal to epsilon x. Again we know the relation that epsilon x is equal to sigma x by E. From here we know that sigma x is equal to minus pxy by ei. Pxy by e. Pxy by I should be multiplied. Now if you want to know ux, definitely we will integrate it and we will get ux. Similarly, let us see epsilon y. Epsilon y is equal to dou uy by dou y. So in our previous classes you have learnt u, v, w. Here instead of u it is ux, instead of v it is uy, instead of w it will be uz. We are not minding uz now. Now dou uy by dou y is equal to epsilon y, which is equal to again epsilon y is equal to nu sigma x by e, that is equal to nu into pxy by ei. Now shear stresses. Gamma xy is equal to dou ux by dou y plus dou uy by dou x, which is equal to tau xy by z, which is equal to tau xy is known here minus p by 2i into c square minus y square, minus p by 2i into c square minus y square. G is already written here. These are the three equations. Now let us try to integrate the first equation. Let us try to integrate first equation so that you will get ux. Therefore ux is equal to minus p. Here p is there x square by 2 integration. Px square into y by 2ei plus some integration constant f1 of y. Now again you have uy. If you integrate y, you will have uy is equal to nu into pxy square by 2ei plus f2 of y. You are integrating this equation, in which f1 of y and f2 of x are unknown functions of x and y only. Now substituting the values of u of x and u of y in equation, this shear stress equation, let us try to substitute. We get instead of u of x minus px square by 2ei plus df1 of, that is function of y, differentiation df1 of y by dy plus nu into py square by 2ei plus df2 of x into dx. That should be equal to my gamma xy, which is minus p by 2iz into c square minus y square. Now you got an equation like this. So x terms are taken aside. When you take x terms aside, minus px square by 2ei plus df2 into x by dx plus new y terms now you are writing plus nu py square by 2ei minus py square by 2iz plus df1y into dy. That should be equal to, here constant term, minus p by 2iz into c square. Now if you look at it, right, this is the these two terms are function. Let us take the first term as f1 of x, second term as f2 of y, and the constant term as k. So f1 of x, function of x plus function of y is equal to some constant k. Now you are aware now function of x is equal to minus px square by 2ei plus df2x by dx. Function of y is equal to nu py square by 2ei minus py square by 2iz plus df1y by dy. K is equal to minus p square by 2iz. Now let function of f1 is equal f of x is equal to k1, function of f of x is equal to k2. Now if you take k1 now, if you take function df of 2 of x by dx k1 plus px square by 2ei. Similarly if you take df1 of y by dy is equal to k2 into minus py square by 2ei plus py square by 2iz. Now you want here what is f, because f1 of y and f2 of x are constants. Now if you integrate it, then you will get these constants. Now f2 of f is equal to k1x plus px cube by 6a plus one more constant, you will get k3 here. Similarly, you integrate f1 of y with respect to y, then you get f1 of y, which is equal to k2 into y as given here, nu py cube by 6a plus py cube by 6iz plus one more constant k4 you will get. Now substituting equations a and b we get. Now let us substitute in the ux equation. Where is our ux equation? You go here, ux is equal to minus p x square y by 2a into f1 of y, na? That you will substitute, you will get like this. ux is equal to minus px square y by 2ea minus nu py cube by 6ea plus py cube by 6iz plus k2 of y plus k4. Similarly, ui is equal to nu into pxy square by 2ea plus px cube by 6ea plus k1x plus k3. The constants k1, k2, k3 and k4 are again determined by our boundary conditions. I said in the earlier boundary conditions at the fixed end and free end. Now at the fixed end of the cantilever at x is equal to L, y is equal to 0. Here we have taken span from right to left. That's why at x is equal to L, your y deflection is equal to 0. And your ux and ui is equal to 0. So substituting these conditions, you will get k4 is equal to 0, k3 is equal to minus pl cube by 6a minus kl1, k1 into L. Now let us take one more boundary condition. Let dou uy by dou x at x is equal to L and y is equal to 0 is equal to 0. So if you use this boundary condition, then you will get this situation. Nu py square by 2a plus px square by 2a plus k1 is equal to dou uy by dou x. But from the above equation, you know that k1 is equal to k1. So if you solve this condition, you will get k1 is equal to minus pl square by 2ea. From the above equation, you know na k3 is equal to minus pl cube by 6ea minus k1l. If you substitute k1 here, then you will get k3 is equal to pl cube by 3a. Also, your k1 plus k2 is equal to minus pc square by 2iz. Therefore, you will get k2 is equal to minus pc square by 2iz plus pl square by 2ea. So, you got all the constants k1, k2, k3, k4. Then again you resubstitute in ux. Therefore, ux is equal to minus p x square y by 2a minus nu py cube by 6a plus py cube by 6iz plus pc square minus pc square y by 2iz plus pl square y by 2a. ui is equal to nu pxy square by 2ea plus px cube by 6ea minus pl square x by 2a plus pl cube by 3a. Now the equations for the deflection curve is, now let us take your deflection at y is equal to 0, because cantilever na you have a point load at the end, then you will have maximum deflection at the end, right? So let us take at y is equal to 0. Your deflection in the y direction, y is equal to 0. Then you will have px cube by 6ei minus plx square by x by 2ei plus pl cube by 3ei. Now your uy at x is equal to 0, y is equal to 0. It will be pl cube by 3ei. So in the starting what we have learnt, cantilever loaded at the end, the deflection is pl cube by 3i. In structural analysis you have determined using elasticity principles. Here we have determined this. This is broadly how we will use structural analysis, theory of elasticity techniques to solve any two-dimensional problem. So with this we have completed our 4th unit. Let us in the next class let us take our 5th unit.